Okay, now we are officially recording. So, okay, in last lecture, we just talked a little bit. We reviewed some material from the statics. We focus on the truss, and the reason is because today we want to talk about the first type of the stress, and yeah, the normal stress. But we need to define the concept of the stress, but since the stress depends to the normal stress depends to the actual forces, so because of this reason, in last lecture, just we a little bit review about the statics, and in the statics we know the problems it's include the actual forces trusses, right? In the statics, the problem include the actual forces would be thrust. The problem, for example, include the shear and actual, and the moment would be the beam frame, right? But we're going to talk about later. But today we want to first of all talk about normal stress just based on the actual load, right? So let me just talk about a little bit about maybe because the concept maybe is new for you, the concept of stress, especially for maybe the people haven't taken about the material lab. So let's go back to the statics, right? So in the statics, if you look at all the problems, right? Just we need element including the force, right? For example, look at if you consider any type of the truss, right? Then we are able to find the forces, and it doesn't matter any value, right? So then it doesn't matter about, for example, sections, right? Because each element has a sections, but we don't know. Maybe the sections would be the cross section would be circle, could be a square, could be rectangular, and the material could be, for example, steel, aluminum, maybe wood, timber, something like that, right? So in static, actually, we don't care about the material, right? And any cross section. The only thing, the important for us in the statics is just to to find the forces, right? So, but then then in the ME304, in the material, we want to see what's the behavior of that, right? And okay, now we know the force. We know the force from the statics, right? And then we want to see, okay, we have this force, and then we have one element, and the element is maybe it's built from maybe a steel, and then also we know the size of the element, size of the cross section, and then we want to see, okay, this element or this member under this force is good, is appropriate or not, right? And then that's the purpose of this class, right? So the other things, only the force cannot give us the element is good or bad, right? Because just assume, for example, you have maybe I have this pencil, right? And also maybe I have, maybe this is my cell phone, right? And then if I apply the same loading on that, right? The same load for both sides, right? Maybe 50 Newton, 100 Newton, right? So then, but just knowing this load, we don't know this load is critical for this member. It makes the crack in this member or makes the crack in that member or not, right? So in the other force, in the other words, so only the force cannot help us to check the behavior of the system, right? Or the element or object, anything. We also need to know about the cross section. We know the material, right? All of them. And then once we apply the force, just once we apply the force in maybe with the both sides, and then the force in the, so just assume the actual loading, right? The force goes to the cross sections, right? And then the force actually distribute on the cross sections, And then if we have a small or weak cross sections and the force is huge, then it may be the problem, right? It makes the crack, or then that's a problem, right? It makes the failure. But if you have maybe a strong member, a strong cross section, then maybe it can sustain about that forces, right? So based on the force and based on the cross sections, right, then we are able to define the new parameters, and that parameter called stress, or maybe in the physics, or you heard about the pressure. It could be the same, but in the mechanics of the material, we don't call the pressure, just we call the stress when we divide the forces to the area, right? That's one thing. So, okay, so now just assume for example, a member of the truss, right? So we have one member of the truss. For example, if you look at the screen, right? Yeah. For example, this one would be a member of the truss, right? Then we have a force here. This is, for example, a member of the truss, right? We have an axial force. The force, it doesn't matter. It could be tension or it could be compression, right? Then when we have this force in reality, right, the force actually distributed on any point of the sections, right? If this is a cross sections of the, for example, element, and then if we have this actual force, this force just distribute at any points, right? And the distributions may be something look like that, right? But the problem is it's very, very, very difficult to find the exact value of the force at any points. For example, find the value of the force at this point, at that point, at this point, that one, right? We need a function, and it's very, very difficult. Therefore, as a simplification, just we assume as an average. So for example, we have a force at this point. So then, for example, in an infinitesimal area here, right? Then for sure, okay, we have a stress at this area. We have maybe a stress at this area. We have a stress at this corner. We have a stress at this. We have a very, very, very small area at each point, right? If we divide these sections to very, very small, maybe 100, 1,000 area, then at each point we have a force, right? And then we can find the stress. But finding the calculating the piece of the force and the piece of the stress is very, very difficult, right? Therefore, just as a simplification, just we assume as average stress, which means we have a forces. So we already find the force from the statics, okay? So we know the forces. We find the force. For example, look at the previous example in the example in the previous lecture, right? So this using the equilibrium equations, method of sections, method of the joints, we find the forces, okay? So we already have the forces. Then the only step is just we need to divide the forces to the whole the cross section, and that stress called the average stress, right? So, but from now, by the end of the semester, then we don't need to say the index of the average or sigma average. Then we can just set average or sigma. We just say it's just sigma or stress, right? Stress or sigma. So but in reality, the stress at any points could be different, but it's very, very difficult to find the value of the stress at any points. Therefore, just use take the average of that. So just we define divide the force divided by the area, right? And then it calls average stress, or then from the rest of the semester, just we set the stress. So once we set what is the normal stress, okay, what is the normal stress because of axial loading, which means the force divided by the cross sections area, right? That's the only things we need to know, right?
So, Professor,
Mhm.
will we not be integrating it all? We'll just be using
No,
the fraction?
no. You don't need to take the integral, right? In reality, that's okay. So in reality, for example, if you have a function of the stress, then okay, then we need to take we can take the integral. It could be force, right? But in practical, which means in this class, we already have a force, right? We already have the force from the statics, right? Since we have a force, just we need to divide the cross section. For example, maybe cross section would be 2 inch by 2 inch, something like that. Then force divided by 4 inches, right? So I want to say this is some definitions of that. You can see all this formula, but the only things we need is just here, right? And also we can ignore this index, right? So the stress based on the actual loading would be just P divided by A. Okay, so okay, now you just assume in the previous in the example from the last lecture, right? For example, if I give you the cross sections for each element, so it's easy. So you can just find the stress force divided by cross section, right? So now there is a maybe there is a one important question. So maybe you said, okay, we find stress. So then what happened? What's the benefit of the stress? Okay, that could be a very basic question that is very important. Okay, let me say something. Once we have, for example, we have any material, right? Then in the material lab, we can put, for example, the sample of the material. For example, maybe could be this is a sample of, for example, steel, something like this, right? And then, okay, we have this sample, we know the length, we know the cross sections, and then we put it under the system, under the compressive, under the tension test, tensile machine. If you pass the material course, you know, but if not, for sure, you can see in the sims, right? And then we apply the loading, right? And then after that, it elongated, and then it's failure, right? Then based on the force applied to these cross sections, we can find the maximum or allowable stress, right? And that allowable stress or maximum one, that was a criteria. Then, which means, okay, if the current element would be a steel, then we can see, okay, the stress for the steel would be, for example, 100 megapascal, the maximum one, right? Then once we measure the stress, if our stress is less than allowable stress, we can say is okay, our, our element is good, is safe. But if the stress is greater than the allowable stress, then that's a problem. Then maybe it's not safe. So there are some appendix, there are some table, maybe in the books you can find online, you can see maybe at the end of the textbook or maybe inside the textbook, right? Then you can see the value of the allowable stress for any type of the material. For example, for the steel with some kind of carbon, or for the maybe concrete, for the aluminum, for the timber, then we have it allowable. Then once we find the stress for our problem, if that one less than allowable stress, then we can say, okay, the system is safe. If it's not, then it's not safe. So then I want to show you some examples, but based on this explanation, all of this, let me ask a question just before going. I want to show some example, but let me ask you just question. I want to make sure you understand something. If, for example, if we find the stress for one member, right? So we have a one member with some certain cross section, we find the forces from the statics. If we measure the stress, and then if we check with the appendix or with the allowable stress, and then if it's greater than that one, right? Which means maybe the system is unsafe, right? Because it's critical, it's greater than allowable stress. So what should we do? What should we do to make the safe condition? What do you think?
Decrease the area, or actually increase the area, no?
Increase the area, exactly, right? The area cross section, right? For example, okay, so P, we find the P from statics, right? So this is, we'll find it. So then we have a maybe cross sections 2 by 2, right? And then the stress is greater than allowable. Then this is not good, right? Then we need to pick the stronger or larger cross section, right? So if we increase the area, which means we increase the denominator, then the stress decrease. Then we need again to check if then the new stress is less than allowable stress, we can say, okay, that's fine. If not, again, we should increase the cross section, right? So, okay, now I think you get all the points. So then, now consider if we have just have only the force, using only the force, we are not able to see, okay, the system is safe or not, right? Because we have force, but also we need to know area, cross section, right? So it's very, very difficult. If, for example, we have 100 ton, for example, for the force, it's different if the cross sections maybe 10 by 10 or 20 by 20 or 5 by 5 or something like that, or 10 by 2, right? So if we picked a stronger cross sections, then it can maybe sustain about that force, and then that's good. But if you pick the weak cross section, then it's not good, right?
Professor.
Yes.
So when the stress is greater than the P over A, that means it's unsafe. So we have to raise the area. That's what. So I just want to clarify that.
Yeah. If the
sigma.
Yeah. If the sigma. If the sigma greater than sigma allowable, right? Then we need, this condition is not good. We need to increase this, right?
Okay.
I want to show you some example. Just I want to ask you after this to make sure you get right. We set sigma allowable, sigma max, sigma yield, sigma ultimate. You will be familiar with all of these things in the material, but I want to also explain some of them, just describe some of them during
Professor,
the, yes.
does the max allowable stress, does it come before elastic deformation or after?
Yeah, I wanna just explain those things.
Oh,
About
okay.
elastic, about plastic. Usually we use the elastic case, but I wanna just, there are lots of things about the stress. Just let me just go step by step. I wanna talk about that one. But in this class, it doesn't matter. We just give you the allowable, or we said that you just compare with that value. It doesn't matter, but maybe we pick the yield stress for in the linear region, elastic region, or maybe we use ultimate for the non-linear region. I want to just discuss about later on that, right? Let me go to, so, okay. The other things, okay, that was, for example, so we talk about this case. For this case, maybe we have a member like that. We want to talk about this, I think maybe chapter 4, maybe, okay? But let me just say a little bit something. So if we may have a member something like that, and then, so if you look at here, the first one, if you make a section at any point, we have just the actual force, right? It's just under the actual. So, but here, if you make a section at this point, right, then since we have a distance between the force, there is arm or distance between the force and this point, we have an eccentric loading, right? Which means we have a moment here, okay? Then we have some additional formula, some additional things to find the stress. We have a stress from the normal, we have a stress from the axial load, and also we have a stress from the moment. So we want to talk about these things on chapter 4, I think. Yeah, chapter 4, once we talk about the beam, right? Okay, now let's just again, just talk about this case, right? Okay, now let's just go to the example. So I want to take your attention. So I want to talk about directly talk about application. Using the stress, we can do two things: stress analysis or design. So in this slide, I want to talk about a slide. I want to talk about stress analysis. What does that mean? In next slide, I want to talk about design. The design maybe is very many people like these things, design. So let's just talk about stress analysis first. So just assume the stress, right? And okay, first we can just first focus on the statics, right? Find the force for each member. This is member AB, this is member BC, right? So you can maybe use the method of joint at this point to find the force at this element and that element, right? So I don't want to spend the time to use the maybe method of joint or something like that, but I recommend you just as a practice, the same as the example in the last lecture, just find the force at these two members, right? These are the results. The result for this one is AB is the 40 kilonewton, for BC is the 50 kilonewton, right? Just as a review, just as a practice, the same as the last lecture, just use the method of section or method of joints, find the forces, right? So AB is 40 kilonewton, FBC will be 50. This is very, very, very easy. The area is much more easier than the problem in the last lecture, right? So, and okay, we are asked, and also this is the member BC, this rod. Member BC has a diameter 20 millimeter. It asks us, is it find stress? First find the stress at this. So then it's very easy, right? Because the force in the BC is 50 kilonewton, right? And what is the area? Area would be just, so how can we calculate the area? What do you think? Area is?
We've got a diameter,
Yeah.
20 millimeter.
Would be pi d square over 4, right? So pi d square over 4, and then we can find it, right? So D is 20 millimeters. So you can, it's up to you. You can use based on 20 millimeter, or maybe just divide the 20 by 1000 based on the meter and put it there, and then you can find the answer. So here, the answer of the area is based on the meter square, which means we do pi times 20 divided by 1000, right? So 20 divided by 1000 would be based on meter. And then you can find the area, right? So this is this area, this value, right? So, and this is the stress. So let me say something first of all. Newton per meter square would be Pascal, right? And megapascal would be 10 times 6 divided by, yeah, megapascal would be the 10 times 6 Pascal, right? If you see kilopascal would be 100 times Pascal, megapascal would be 10 to the 6, right? So that's something we should know in the SI system. Maybe you know about the unit is the same as the unit of the pressure, right? We can say, so in the US system, we can say PSI, KSI. In the SI system, it's said Pascal, maybe kilopascal and megapascal, something like that, right? Yeah, just be familiar. Okay, so again, look at this one. Look at this figure. This is the force, and this is the stress. And again, you know, you can see it doesn't show the average because we said always we assume as average. So this sigma in reality we assume as average, but we don't need to show, right? Then we said this stress means average, so but we don't need to say. So so this is so it's very easy to find the stress. And now, okay, maybe from the experiments from the lab, the allowable stress also is given, right? The allowable stress is 165 is given. So therefore, we can compare. So what do you think? So yeah, 159 less than 165, right? So that's okay, which means the member is adequate, is proper, right? If we find the stress and it's greater than 165, then which means the member with this 20 millimeter with that diameter which is not good. Let me, there is a chat question. Was that the area? Okay, you mean? Yeah, this area is the area of the area of the circle, that's cylinder, right? This A, because the diameter of this is 20 millimeter, right? So the area would be just pi d squared divided by 4. That one. This area is just area of the cylinder. This cross section, the cross section of this is something like that, right? You can see this. So this one, yeah, this. The pressure have units of the unit of the force have Newton, right? The pressure or stress, the unit is Newton per meter square or Pascal, right? So let me write here. This one is Newton for the force, and the area is meter square. So Newton over meter square calls Pascal, right? That calls a Pascal. Megapascal means if we have a huge number, then we can divide it by 10 to the 6, then we can say that's megapascal, right?
Hey, Professor.
Mm-hmm.
Can you explain why you used 50 kilonewtons instead of the 40?
No, it asks to use for this member BC. This is member BC, right?
Oh, okay.
Yeah.
I assumed that the thicker
No,
cross
this is
section meant that it would have
A,
bigger.
BC. Yeah, the problem is set check for BC just. This
Okay.
is member BC, right? This is,
Thank you.
this is member AB.
Professor,
Yeah.
where did we get the 165 from? The MPA?
165 is given.
That's given?
Yeah, it's given from the maybe experiment from the lab.
Okay, thank you.
Mm-hmm. Area, that's the area of the circle. Area of the circle is pi r squared, or even instead of r put P over 2, right? Yeah. Guys, if you ask me, just is better than chat because then I can answer it quickly. Right, and then, does it make sense to you? Does it make sense?
Yes.
Yeah, just ask me what voice is better than the chat. Okay, so let me just, the problem is when I use it in the Zoom, if I will go to the next slide, we can see these comments. So, okay, that's okay. Yeah, if your mic is not working, that's fine. That's good. Yes, you can. Yeah. F over A, P over A, it's the same. Actually, this is a symbol. P, this P means this F, right? P over A means P is equal.
P is force.
P is force, right? Stress would be force divided by area, and P in this case would be FBC, right?
Like pressure.
P is force, F is force, so sigma is stress or pressure, right? So let me in this class, when we said F and P, these are forces, right? These are, all of them would be force in this class. Once we said sigma, sigma could be, sigma is stress or pressure, but let's just forget about the pressure because for all the semester, we're gonna say just stress. Forget about pressure. But pressure and stress would be the same. But when we said F and P would be the force, right? Does it make sense to you?
Yep.
Okay. Let's go to, I know it's at the beginning of the semester and there are lots of concepts, maybe it's confusion. So let's go to the, okay. This type of problem called stress analysis. Let's go to the next problem. Next application would be design. So what does that mean? It's very interesting, actually. Okay, let's back to the previous one. You know, here, look at this case. Sometimes we already have the structure, right? For example, we already have this truss. We can use the P or F, it doesn't matter. For actual force, we can use the letter P or F, it doesn't matter. In the textbook, for some example, use the letter P for the force and or use the letter F. In the statics, the actual force, so in the statics we said force, but once you want to categorize in the actual and shear, in the actual force, maybe we said P, for a shear force we said V, but all of them are force. So for some example, maybe we use P, for some example, we use F, right? So it doesn't matter. You can use P or F, it's the same. Does it make sense to you?
Yes.
Okay, it doesn't matter, so yeah. It's as a symbol. So in this problem, with stress analysis, we already have the sections, right? For example, we have these structures, it's a current structure, and we know the section. And then we want to check, is it a good or not if we apply the force here, then okay, we find the stress, and then we compare with allowable stress, and said, okay, this section with this diameter is good. But sometimes we have a problem like this, and in this problem, there is something, I think that the textbook did something wrong here. There is there is no diameter. Diameter for is B is not given, right? This is done. So for example, we have this structures, right? And we don't know the cross sections, right? And the purpose is to find the cross sections, to find the diameter, right? This type of problem called design problem, right? Which means look like this. For example, we have a pure ground and we want to make a building, right? We want to make structures, which means we want to design the cross sections. We want to find it and which section is good, right? That type of problem called design. So therefore, okay, we have an allowable stress, right? Allowable stress is given from the factory, right? And we know the allowable stress is the stress we cannot exceed that, right? That's the maximum value, right? So based on the allowable stress, based on that stress, then we can find the cross sections, right? So if sigma equal P over A, then A is P over sigma, right? P is the force around the statics. So we already have it, right? So look at this member, and the force is 50, right? In the previous slide, we know if you solve this problem by statics, we already know the P is 50, right? So that's fine.
I'm so sorry. Can you go back to the analysis? I'm kind of confused on one thing. On
Okay.
the previous slide.
What's your question?
Like, how did you know that it was good or it wasn't good? Like, how did you? Is it because of the 159 was less than the 165?
Yes.
Okay, I just want to clarify. Sorry, thank you.
Yeah. Since it's less than that one is the good. Okay, in the design case, we don't have the cross section and we want to find the cross section, and the criteria is sigma allowable, right? Because sigma allowable is the maximum stress, right? So then we can find the area, right? So we have a force divided by a stress. Then we find A, and A is pi d squared over 4. Then we can find the diameter, right? Using this calculation. So, and now that's a question. Okay, we find the diameter, but in practical, we don't have the member width 25.2 millimeter, right? Then we should round it to some standard diameter. So we can pick 26 millimeter or 27 or something like that. So let me ask a question. Why not 25 millimeter? Why 25 millimeter? Why it pick 26 millimeter?
It would fail at 25.
What did it say?
It would fail at 25.
Yeah, because 25 is less than 25.2, then it would be fail, right? Because this D is the minimum value that we can just design it, right? For the D less than that, the system will be failed, right? So we find 25.2, this is the good one, but in market, we don't have this diameter, right? 25.2 millimeter. So we should pick some diameter greater than we already know in the market. Maybe we don't have also 26, maybe we have just 30 millimeter. That's fine, we can pick it, right? So that's a design problem. In the design problem, we don't know the cross section and we want to find the cross sections, right? So just we know, okay, cross section could be a circle, then we need to find the diameter. it depends of the application. It depends of the right? Yeah, it depends of the type of the application, right? If the application would be maybe a steel or concrete or aluminum, it depends, right? But and based on the application, sigma allowable is given, right? The sigma allowable is different from material by material, right? So that could be a design problem, right? So, you know, stress, sometimes like this problem, this is a current structure, for example, we already know the diameter, right? So then we find the stress and then we can compare with the allowable. But sometimes we said, okay, sometimes that's a new structure, we don't know the diameter, we want to find the diameter, right? Then we can use this formula, just we use the maximum stress here and then find the minimum value for diameter, right? Does it make sense to you?
Yeah, pretty logical.
Mm-hmm. Yeah, so let me go to the next thing. So, the next things, yeah, I want to talk a little bit again about some things, and then maybe you can continue for some other example next lecture. But let me say, talk about another type of stress. It's the shear stress. Let me, okay, maybe you can see me now. So sometimes for the shear, so, you know, if you again go back to the statics, so in the statics we have actual force, right? And also you have a shear force, right? Shear force. So for example, if you apply the force here, maybe we have this object, this AB, this member AB, and we have two attached objects. So we have two forces here, maybe these two forces here. And then if we apply these forces, maybe we have some crack here, maybe there's a failure in this member, right? Then, which means these forces play the role of shear force for this member, right? So we have this member and we apply the force here and there, and then maybe it makes a failure here. So then this force is look like the shear force, right? It plays the role of the shear force, right? These are all these things you can see also in the statics, right? In the statics. So that's a definition of the shear force, right? The shear force are applied transversely to the member, and here they have a member AB, right? So since we have a shear force, also we can define another type of stress as a shearing stress. What does that mean? Look at this force P here, right? This force goes to these sections, right? For example, like this. Look at, I don't know, can you see my hand? So for example, this hand would be, for example, force. This hand would be the cross section, right? So this force to these sections, that it makes a stress, right? It makes a stress in this surface, right? For example, like this. Here, if I apply the force here, right? Then this surface is under shear. Can you see me here?
Yeah, we can see you.
Yeah. So if the force look like this is normal stress, right? We already discussed. If the force look like this is shear force, and it makes a shear stress on this area. So again, if this is the normal, actual, this is actual, we have a normal stress on this. If this is the shear force, we have a shear stress here, right? And the formula is the same, just P divided by A. Again, we set average because to find the stress at any point is very, very difficult. So just we use the average. Also, we said the shear. We said average stress there. So, and again, by now, then just we remove the index average. When we said the shear stress, we know that's average, but we don't need to show this index. If you set the normal stress, we already know that's the average one, but we don't need to show, right? So guys, do you know what's the difference between shear stress and normal stress? Does it make sense to you?
Yeah, I just
Yes,
want
sir.
to
Yeah.
so a shear stress is like if I'm pushing a sandwich, the sandwich is going to topple over, but a normal stress is like I compress the sandwich.
Right. Yeah.
All right, appreciate you.
Yeah. Yeah, you are right. And also we have some type of shear, for example, since you said sandwich, maybe some circle based on the torsion. We want to also talk about maybe later on. But here,
Professor,
say that again.
I have a question.
Yeah.
So is this figure above 1.14, is that supposed to depict shear stress? It looks like normal to me.
Okay. That's a good thing. Good things. This P. Okay, let me annotate here. This P on here is normal, right? Because it's a surface, right? Is normal. But but now ask you if we want to focus on member AB, right? The force is here now. That's the same force, right? Because of the equilibrium, this force goes there. And the force P for these sections play the role of shear, right? For this surface, that's good. This is actual, and this is we have a normal stress for this surface. But for this surface is shear, right? For this
Okay, that makes sense.
right? For this surface is shear, and actually, yeah, because we wanna talk about member A, B, right? But yeah, you are right. If somebody said, okay, we want to focus on this member, let's, for example, member CD, something like that. Yeah, we said, okay, this force play the role of normal. And actually, your question is very good because next week I want to solve some problems, and the problems actually is very complicated. And we have one single force, but for one element it played the role of normal. For one element, it played the role of the shear, and for some element, it played the role of bearing stress. I want to talk about bearing stress also later. Okay?
Hey, Professor, is a good example of shear stress like tearing a piece of paper?
Yeah, it could be, yeah.
Like using scissors.
Yeah, something
more like cutting.
Something like that, maybe. Yes. These are, for example, under the shear, right? Under the shear, right? This could be like this. Does it make sense to you?
So basically, there is no opposite or opposition force acting on the
exactly
top force, right?
Yeah, for normal stress, force is
kind of
perpendicular to the surface, right? But in shear stress, force in the direction of the surface, right?
Yeah.
Normal would be like this. That's normal stress, right? In the previous slide. For shear stress, we may have, if this is a force, and again, we have this surface. This is shear stress. It looks, maybe the good example could be, for example, if you look at the beam from the statics. Let's, for example, from the statics, we have free body diagram for beam, right? Something like this, right? Then if you remember, we write something like that, right? This, and if you look at this surface, right? And this force could be, it provide the normal stress on this surface, but this force could be the shear stress on that, right? Does it make sense to you?
Professor?
Yes.
But would it be, I thought for shear force, it has to have two forces going in like the opposite direction. So how would that one be shear?
Not necessary. We want to talk about, let me say, I know what you are saying. It may be confusing. Let me a little bit back to the statics and just maybe a little bit talk about, so you say about these two, but we have here, I talk about this bit. Let me go to the whiteboard and say some general things. Maybe you forgot the statics and it would be so helpful. Let me go to the whiteboard. Can you see this whiteboard?
Yes.
Okay, I want to say some general things, not necessarily those two forces or three. Let's assume, for example, we have some beam like this, right? Some general, maybe something like that, with different type of forces, something like this. Maybe we have force like that. We have force here, right? Bunch of forces. It doesn't matter. We may have force like this. If you remember, so these are all of these called external forces, right? These are external forces. And if you remember, once we want to analyze the beam, we need to make a sections and find internal forces and then find those forces, and then we can draw the diagram or something like that. So, but we don't want to go to all the details. But let's just, we wanna talk about some arbitrary sections. For example, maybe here, maybe these sections. What does that mean? Maybe some people, some guy maybe ask us, okay, find the stress at this surface, at this section, right? Or find the forces. So, okay. Just we need to again draw the free body diagram, right? And at the first essay we find the reactions. I didn't do that, right? So let me just see. So for example, we assume we already find the reactions. We have these reactions. The free body diagram here, we have this force. We have this force, right? And then, okay, we already know there is a shear force here, right? And using the equilibrium summation of, for example, force in direction of y equals 0, for example, this is shear force, right? Then we can find this V, right? It could be a value for this V, right? Does it make sense to you by now?
Yeah.
Does it make, okay. So these are the statics case, right? Okay, now, okay, we have this force, this shear forces, right? Okay, for the mechanics of the material, for this class, for the shearing stress, we have this one. And then we said, okay, shearing stress would be tau V divided by this area. We don't know what, but for sure it's given, right? So what does that mean? Which means, so we have this problem with external force, then we make a section and then we find internal force. That's this shear force is an internal forces, right? And then divided by A. So then maybe Another guy said, okay, I want to find the shear stress at this section, for example. Then we said, okay, take a free body diagram. So we know these reactions, for example. We know this one. And then this is, for example, the shear force, for example, like that. And then here, write the summation of force in direction of y0. And then we find V. And then for this section again, we can find V over A. So I am saying all of this, which means don't care about the external force or how many forces we have, right? It different problem by problem, it different, right? So in this problem, we have 1, 2, 3, 4, 5 external force. So we have also 2 reactions, right? In the problem, in the slide, we have only 2 things. And I know they provide the shear stress, but the approach to find the force is something like this. First of all, we should solve the statics problems, find the V, and then go to the equations. So then let's back to that slide. In this slide, okay, we have this problem. We have these 2 external forces, and then we have, so this P here is the internal force at this section, right? But in this problem, since we have only 2 forces is equal, then for sure this P is, this shear force is equal this one. But I want to say, so don't memorize the thing something like this. Okay, we have these 2 and then the shear force is equal this one. The reality is we should first make a section at point C, something like that, and then write the summation of force in direction of y0, find that. So the textbook says this is just focus on the mechanics of the material. It just escaped the previous steps to find the equilibrium, to write the equilibrium and find the internal force. And so it just picked some easy problems and then said, okay, we have these 2 forces in opposite directions. So we have this shear force and then put it here, right? Because now we're just focusing on this formula. But now your question is a good question. It's focusing on the statics. So, but now, which means if we have any problem, any other problems, not necessarily like this, maybe a bunch of forces. First of all, we should find the shear force at individual sections and then use that force to solve the problem. But in this problem, the shear force here, okay, here is exactly the same as this one, these forces, right? Is exactly the same because, so we want to solve some problem later similar this one, some simple cases, because for sure in this class we don't want to focus on very more complicated, because if the problem is lots of forces, is more complicated, which means we should spend some more time to solve the statics problem and then goes to material problems. So it takes time. For sure, we want to solve some problems similar, something like this. Is more visualized. Look at the forces, then you say, okay, these forces makes the shear, and with the same value. But keep in mind, it's not exactly this rule. The procedure is, first of all, we should analysis, find the forces at any sections, and using the equilibrium, and then use this one, right? We're going to talk about the more details in some example. Does it make sense to you, these things? Does it make sense to you? Can you see that?
Yes.
Yes.
Yeah, in these initial lectures, I want to just make some bridges between statics and material, because the textbook assumes we know all the statics, so that it skip the previous things from how to measure the forces. It just focus on the material formula. But now, since we wanna discuss about the forces and later moments. So for sure, we need some knowledge, strong knowledge about the statics to solve it. So, and in the, for example, for the problems for the, for example, test or homework, we have maybe two types of problems. For some problems, exactly the forces are given. So just you need to formula. For some problems, maybe not, which means first of all, you should solve the problem by the statics, find the forces in elements or in the section, and then use this formula to solve the problems, right? So do you want to continue or you're tired?
Continue.
I'm tired.
Okay, let me say a little bit about some examples, but I will repeat it also. So I don't want to go to other details. Let me just one more slide because it's very similar. So let me just focus this one and then kind of stuff. So we have two types here, maybe single and double. Single, maybe some application like this. So you have a board and we have these two forces, the same force in opposite directions, right? And now this forces goes to this board, right? And then it makes this section of the shear, right? So these two forces in opposite direction, it makes the shear, this section of the shear. So this one called single shear. But if you compare with this application, right? If you compare with this application, if you apply the force here, and then this force goes to these two plates, right? These two forces from these two plates, right? And then it makes two sections, maybe two sections of the shear. This one called double shear, right? So which means here, if you look at there, if you make a section at here, then the internal force, look at the internal force, P. P is just equal F. But here, if we just draw the free body diagram at these two sections, we have this F, and these are the internal forces, and the internal force is half of the F, right? This is just a difference between single shear and double shear. Just look at these two applications. You can see, so if you have applied the force in these two plates, right, then it make a crack at the middle. But if you apply the force at this plate, then it makes a crack at this point, right? It makes, let me annotate, it makes the crack at this. Sorry, it's my drawing was not good. It makes the crack here and also make a crack here. It calls like this. It calls double shear. Single shear, right? If you have two forces here, just make a crack maybe here. That section, right? A single shear, that's double shear. So the only difference, so for the equation, in the equation I discussed in a few minutes ago, just force divided by area, right? So internal force divided by area. Here, internal force, equilibrium, P equal F, just F divided by A. But here, equilibrium, F equal 2P, right? Therefore, P is F divided by 2. So then the equation would be, look like that. So that's the difference between single shear and double shear. Just, you should just realize the application. Just assume that's a real problem. Now, if you apply the force to force here, then it makes a fracture here. But here, if you apply this one, then the force transfer to these two plates, then it maybe makes the crack here. Then we set the double shear, and just the only difference for the formula to find the stress for the single shear, just P is equal F. But for double shear, since we have two surfaces, right? And this is a free body diagram, and the internal force, because we need to divide the internal force divided by A, the internal force would be the F/2, right?
Professor.
Mm-hmm.
So the P over A is the general case, and the F/2A is the specific case.
P over A, P would be the force in the sections, right? And you are right. In this case, P would be F/2, because F is external force, and we use the equilibrium, find the P based on F, and is F/2. You are right. P over A is the general formula in that section, right? And then based on the value of the external force F, then we are able to measure P, right? It look like this. Let's again back to that static problem. It's very interesting. Look like this, right? Look at this one. This is F1, F2, F3, F4, F5. These are the external force, but this V or P, that's the internal, which means this is V is a general things we need. And these are F, it depends of the problem. Maybe this is F1, this is F2, this is maybe F3, but we need to find the force in the section, that's a shear. And in the textbook, it write P over 8, but right here, F, V over 8. And in the, can you see the slide?
Yep.
Yeah, and here, the external force is F, but the general formula is P over A. We find P based on F. Here, P is equal to F, that's fine. But here is P is F/2, right? These are some two cases. We have some examples about these things, and also I upload this PowerPoint in the Blackboard, so you can all. Next week I wanna talk about the next slides. So there are some other things, but now I think these are some enough, and so. And we need to solve some examples, some problems to reach the homework. So, but now, so this week, I recommend you please just review this concept, and especially review the statics to find, for example, method of joint, method of sections for the truss. Solve some examples. Just solve some example problem with yourself, and just make sure you can analyze the truss. Just solve something. You don't need to spend much more time. Just look at your lecture notes if you have some sample problems, and just review these problems. And next week, you wanna solve some bunch of problems. And again, the initial lectures is very important for this class, because we wanna solve, and maybe some more complicated. And after some time, then the course will be relevant. So. Let me stop recording. Then if you have any question, then again, you can ask me, but let me just stop recording.